Hi everybody, and welcome to part 2 of the Kenwood KA9100. And wow, what a bunch of responses I got to that first video. First thing I want to do is thank a whole bunch of you who kind of gave me a little tip on this that I didn't know. And that is, these transformers actually have a thermal fuse inside of them. Now, I really never thought about these ones, usually these smaller ones, having that in them, but apparently they do. Now, a thermal fuse is just a small device. It's not very big, little square thing with two little wires, and they usually put it inside. It can be buried inside the windings, or it can be right underneath the final tape wrap inside the transformer. And the whole point of it is, if the transformer overheats, that heat will actually cause the fuse to open up, which will protect the transformer windings. Now, normally when that happens, there's a couple different failure modes of that fuse. They can fail, number one, just by age, just from thermal cycling, and then after a while they just open. They can fail from actually doing their job. If the transformer is overloaded for a long period of time and the coils get really hot, the fuse opens up. And the third thing is the actual current can be too high. So if you exceed the current rating of the thermal fuse, the fuse will open again. For instance, if you had a really hard short or something. Now, it's kind of weird that that opened up the way it did, being that you have a 2.5 amp fuse at the mains, feeding it. But again, these can just fail from age and from thermal cycling. And this also is the same side that the chip, the Darlington Power Pack, or whatever you want to call it, the amplifier module, that's the same side that failed on as well. So probably what happened is, I would say the module probably failed because the amplifier was under heavy load. That short actually caused a shock to that fuse, and the fuse popped before the actual filament fuse popped, the little glass fuse in there. Glass fuses, they don't always fail very quickly. Unless you have a catastrophic overcurrent situation, the fuse can actually hold for a while and carry current in excess of the fuse's rating. So this is a 2.5 amp fuse. It's not uncommon to have double that on it for a short period of time or more, and the fuse won't open. So what may have happened is, if this truly does have a thermal fuse, this went before that. It's just the way it happened. Now, I know some of the bigger amplifiers had that. For instance, the Marantz 2500 that I did, that has an enormous toroidal transformer because that's a very high-powered amplifier. And it notoriously has the thermal fuse in it, which is a good thing. But the transformer, they potted the transformer. So they took this toroidal transformer, they put it in a metal enclosure, filled it with potting compound, and they basically potted the fuse right in there with it. So really, the fuse is a moot point because, if the fuse fails, it's the same as the whole transformer failing, because that potting compound is really difficult to get out. But anyway, several of you mentioned this. A couple of you asked if I've checked that, which I hadn't. And then I think 2 of you commented that you actually have seen it in the SA9100 or the KA9100 amplifier transformer. So we're going to pull this transformer out, and we're going to check that out and see if that's what it is. And if so, we're going to see if we can repair it. All right, we got all kinds of pictures here from different angles. And I just, a couple of the wires I unwrapped, and the rest of them I had to just clip and mark them. And we have plenty of length for that. So we're going to take these 4 nuts off of here. remove the transformer, and we'll see if this has the thermal fuse in it. I mean, that's, wow, thank you guys. Again, I never really thought of that in this particular unit, but it makes total sense that they would. Now, again, if the fuse opened up because the transformer was grossly overheated, there's a good possibility that the enamel on the windings has been damaged and burned. And even though the fuse opened up, the transformer itself would still be bad and need to be replaced. But hopefully all that happened was an overcurrent situation. I mean, that's a huge transformer for just a single 90-watt amplifier, a mono amplifier. So hopefully that's a different size. So let's see here if I have the other one that goes on there. If that's 7mm, yep. And hopefully this is all there is to it. Now the other thing you have to watch with old transformers is if the enamel or the varnish on the laminations has broken down and causing the laminations to short out. And what do I mean by that? Well, transformers, the core of the transformer is not a single piece of steel or iron. It's actually many thin sheets that are laminated together through the transformer, and that actually helps reduce the effect of the eddy currents in the core of the transformer. If you had one giant chunk of metal there for the core, the eddy currents in the transformer would cause it to be very, very inefficient. The transformer would consume a whole lot of energy and convert it into heat pretty much through the eddy currents. And what happens is they make the core of the transformer out of a bunch of thin laminations that are they're called EI, because the one is shaped like the letter E and the other one is the letter I, and that E shape goes through the core like that, and then an I shape finishes it off on the end. And then the next lamination, they flip it the other way, so the E goes this way and the I's on this side, and they alternate back and forth. And each one of those little sheets is covered with an enamel or a varnish, kind of like the enamel of, a piece of magnet wire. And that keeps those plates from electrically contacting one another, and that reduces the effect of the eddy currents. And what happens is if that varnish breaks down, it'll basically cause those plates to short out against one another, and it will make the transformer much less efficient. The transformer, while during operation, will actually run much hotter. So if you have a transformer that's running really, really hot, even though the circuit is not drawing a lot of current, it may be that your core of your transformers, the laminations, are shorting out. And that definitely can happen to an old transformer. So you have to kind of watch out for that. I'm hoping that's not the problem with this one. But I mean, looking at things like this, when I see this kind of, it tells me this thing was hot for some reason. But I'm really kind of excited to see if we have the thermal fuse in here. That will be great. Again, I don't know how accessible it is. Sometimes they're really buried down in the coils. See how this has that copper shielding around it? So getting into that might be a little bit of a challenge. All right, well, if I'm going to screw this up, I'm just going to go ahead and screw it up on camera. So I got to move the camera out of my way so I can get close enough to see what I'm doing. And all I'm doing is I've bent this copper shield up a little bit. I don't want to take this too far apart if I don't have to. And I'm going to cut off this little piece of tape, or maybe not. I have this side cut already. And I'm going to try to open up this. The primary wires are these two right here, and they go onto this end, and I can see them bending over. What I cannot see yet is any type of thermal fuse, but that doesn't mean there isn't one in here, and it doesn't mean that it's just not down in there a little bit further. I don't want to have to tear this whole thing apart if I don't have to, unless it's really necessary. And I'm just using some different flat tools to kind of pry open some of this varnish, because this is a varnish dip transformer. This is actually a really well built transformer. When I was doing an internship, I worked for a machine company that did transformer and mostly motor rewinding, and watching the process. What a difference between a well-built motor and some of the cheapy ones that you get. Big difference. And one of the main differences was how they were varnished and so forth. So here is the black lead of the primary, and here's the white lead of the primary. So that's these two right here. Let's get our meter and see if we have any kind of continuity. Just interested to see. We in shot here? Oh yeah, we are. Okay. All right, so let's go here to here. And you can see it's wide open right there. Pretty tricky. Well, let me make sure that I'm on the right leads. Oh, I'm sorry. It's the red and the white, not the black and the white. Black is your center tap, so that's the center tap. So it's the red and the white. It's this one and this one. If I read from here to here, still wide open. See? There's 0 volts. And there's that. And there, oh yeah, look at that. Right there. I can just see it down in there. Can you see it? I don't know if I can get a flashlight, maybe you could see what I'm talking about. See, right there's your thermal fuse. There is one. Look at that. It's right, if I point at it with this meter probe, it's right here. I'm actually touching it with the meter probe right now. So maybe that's our problem. Now here's the thing. Is it going through to the other side? And if it is, can I possibly bypass it? Boy, would that be nice. So I think what I'm going to do is I'm going to take this tape the rest of the way off here, like that. And take this like that. I'm going to get this out for right now, and I'm going to take this wrap off just out of the way, and I'm going to try to get to this and get it out just the same way, like so. I don't want to force anything, I just want to take my time. And maybe, just maybe, that wire will be coming out the other side here. Wouldn't that be wonderful? Had a weird problem at work today, and my engineers scratching their heads for a little bit on a unit. It kept popping the breaker, and as it turns out, it was the breaker. How about that? Okay, so is that perhaps this the wire here? So like one end, that sure looks like it. So let's see if I go from up here, right here, to the white lead over here. And look at that. If I go from there to there, and sure enough, we have a bad fuse. Thank you, fellas. All of you folks. Thank you, thank you, thank you. It is the whole reason that YouTube is just completely awesome, huh? So let's do this. I'm going to delete this fuse, is what I'm going to do. And in order to do that, I'm going to give this a little cut right here. Let me back you up. I'm going to cut this off clear down at the bottom where the fuse is. And that fuse is just going to, since it's open, I'm not really worried about it. I might put a little heat shrink over it or something, but I'm really not going to worry too much about it. Okay. And we just want to get this to go across to here. And I'll tell you how I'm going to do it. I have some nice, let's see here, there's 22. I think I might even have some 20 gauge somewhere. Let me find some bus wire. Hold on. Okay, so here's some 20 gauge bus wire. And I'm just going to take a piece of this. You can see it's just 20 gauge bus wire. I'm going to cut a piece of that off. Put this back. And I'm going to just go ahead and first thing we're going to do is we're going to start a wrap on it. So you can see what I'm doing. I'm just spiral wrapping this around here. Hopefully I used a large enough screwdriver to get this over here. And if not, we'll just give it a little reverse twist. Like that. I'm going to put this over here like so. Kind of spiral it down on. Just like so. And then just, I want to make a good mechanical connection first. And then I'm going to take the soldering iron. And I'm going to do this like so. You can see that's right on there. And let me get some heat shrink. Okay, I'll put some of this thermal sleeving on there. This stuff's pretty good. And then what I'm going to do is I'm going to run this up through here, if I can get it to bend through how I want it. Just like so. I want this to go over top of the smaller stuff. If I can do. Okay, that's what I want. Let's see if I can get that down a little bit further in there. Okay. And I'm going to take this, I'm going to bend it around here one time. And again, yes, if this transformer overheats, there is no thermal fuse now to protect it. But that's not a great big deal, because I really don't think that is going to be a big issue on this. Because technically, this thing doesn't appear to have overheated. You can see the scorch marks in the varnish and on the tape and so forth if these overheat. So this thing did not overheat. That fuse went because it just wore out and it blew before the glass fuse. And I think that was that's your whole problem. So I'm not gonna sweat it too much. There you go. And I'm going to bend this back down like this and fold everything back over. And what we're going to do is I'm going to take some of this Kapton tape and I'm going to re-insulate it with a few layers of this stuff right here. And then I'm going to fold this back over. And I'm going to see if we can kind of varnish that back over again. We'll see what happens. And see if we fixed it. Okay, now that I have everything in this general area, before we put it together, let's make sure everything's good. And there it is. Yes, it is. So, all right, I will put several more layers of that, then I'll fold this outer part over. Okay, there's that side. And I've put some fresh Kapton tape on this side. I'm going to go ahead and fold this under the way it was. Just like that. And then I'm going to take this piece, put it back in here, and I want it to go over top of this tape on this side. And I may have to move the camera to, nope, I got it. Just like that. And I'm actually going to fix that with some adhesive so it doesn't move. And then we're ready to put it back together. Okay, it's all put back together. I think it turned out pretty good. And I put some fresh varnish down inside here, so when that dries, hopefully that'll harden and kind of bond back to the copper. And I formed that back down. And I think we're ready to put the top back on and put the bell ends back together, and put it all back together. And I think while I'm at it, I'm going to give this a little cleaning before I put it back in because, well, it's messy. Well, we have a little visitor. Hey, Mango. What? What? What are you doing? Huh? What's going on? This is Mango. We adopted her about a year or two ago. Huh, babe? And you miss your owner, huh? You miss Susie. She's not here, huh? I hear you. Come here. Come here. Hi. How are you? What? What are you going to say? You going to talk to somebody? You going to talk to the people on the camera? Huh? Yeah? Huh? Yeah. You probably want a kitty treat, don't you? Those are upstairs. We don't have anything down here. Okay. Okay, so I've scraped and hit that with some 220 sandpaper, wiped it down with some acetone, and I think I'm just going to put a quick coat of paint on there, and I'm not going to spray it because I don't feel like spraying paint down here. So I have some Rust-Oleum that I'm going to borrow from my wife. Don't tell her. I'm just going to lightly brush some on there. If there's a few brush marks, I don't really care. They should pretty much work out. If it looks bad, I'll get the lacquer thinner and take it off and take it to the garage and spray it. But I just don't want to have to go down there if I don't have to. And we'll put it back together. Okay, after a little bit of paint, it turned out pretty nice. And yes, I know all about the oily rags and the spontaneous human combustion and all that stuff. So no need to warn me of that. I definitely will take all the precautions. And when this dries, we'll put it back together and I think we'll be good to go. I don't think I really need to paint the end bells because they're pretty good. There's no real rust on them other than dirt. So they just need to be cleaned up a little bit and they'll be okay. Now the big question is, do I want to pull the other transformer out and paint it? It's more of a hassle than anything else. I mean, it looks ugly, but I don't know. I'll think about it, which probably means I'll end up doing it, but oh well. Okay, we'll be back when everything's dry and back together. Okay, well, this paint is still a little bit sticky, so I'm not ready to put it back together, but I figured while we're in here, we'll do a few tests, and we'll make sure our transformer is working. So the orange leads are the B plus and B minus leads, or that goes to the B plus B minus supply, the big power supply, with the black lead being the center tap. So from the center tap to either orange lead is where you're going to have, what they're saying in the schematic is 43 volts AC. Okay, and that's if we have a nice solid 120 volts going in. And so if you go from the orange to the orange, it should be double that. So you should have somewhere around 86 volts or so. And so I have my voltmeter connected. And I have the kilowatt. We're plugged into the kilowatt. So we can actually monitor a few things when we turn this on. So let's flip this on. And you can see we have 120 volts. And we have just a little bit over 43 volts per winding. And that's about what I would expect. There's no load on this right now. So it's 87.6 volts, 120 volts going in. If I look at the watts, it's drawing about 3.1 watts at idle. So the transformer itself, just the losses in the transformer, are drawing 3.1 watts. But there's a little more to that. If we go to the VA rating, it's actually higher. You're actually dissipating about 8.6 volt amperes, okay, or VA of power. And why is that? Well, what is VA in the first place? So VA, or volt amperes, is going to be the voltage times the amps, okay, which is similar, which is what watts is in DC terms, right? Volts times amps, times the power factor. What is a power factor? Well, a power factor is a kind of a fudge factor number that you put into this formula, the wattage formula or the power formula, to compensate for the reactive losses in the circuit. So because a transformer is actually an inductor, it's going to induce inductive reactance onto the circuit, meaning the current and voltage are not going to be in phase with one another. So let's back up a little bit. If I were to connect just a resistor across this mains line here, get rid of the transformer, just put a resistor, the current and the voltage are going to track with one another. So as the voltage goes up, the current will go up with it. As the voltage starts to drop back down, the current will drop down with it. Now, here's the thing. When you start adding inductors or capacitors to an AC circuit, Eli the Iceman shows up. What is Eli the Iceman? ELI, remember this. L, which is an inductor, E leads, or voltage leads current, or E leads I. ELI, Eli. And in a capacitor, C, ice, I leads the voltage, right? Or I leads E. So the bottom line is they're the opposite of one another, but they both do the same thing. They cause the voltage and current to be out of phase from one another. So what you're seeing right now, if I click on this power factor, the power factor is that correction that you're going to have to factor in if you want to get the actual wattage of the circuit. So the power factor, according to this, you can see it's 0.36. So let's write that down for a second. And let's just see if this is lying to us or not. Okay? So 0.36 power factor. And if we go over and we look at our volt amps, if we take our volt amps times our power factor, use our calculator here. So we have 8.6 VA, or volt amps, times a power factor of 0.36. It says that we should have somewhere around 3.1 watts of power. And when we switch to watts, how about that? The math works out. Amazing, huh? Conversely, if you take that wattage and you divide it by the power factor, right, you get your VA rating. And that's the relationship between your volt amps and your watts. This power factor that you're looking at here is that the influence of the, in this case, the inductive reactance on the circuit. Okay? So right now, the load that this is going on here is it's mostly inductive load. You see that? That's what that 0.36. By the way, a power factor of 1, okay, or unity, that power factor of 1 means that there is no reactance in the circuit. So if I were to put that resistor on here once again, that power factor would change to 1 because it's purely resistive. There's no reactive load on it. Let's do something else now. Again, we have that 87 volts, all right? And I have a light bulb over here. And it's just a little 40-watt bulb. And if I put that light bulb on the output of the transformer, all right, first thing that happens is you drop about a volt because now you're putting a load on the transformer. But something else happens. If you look at your power factor is now almost 1. See, 0.98. So it's very, very high power factor. It's almost a perfect 1. But it is not quite 1, if you notice that. If I go back to our watts, right now it's 39.4 watts. Okay? And if I go to volt amps, 39.9. See, the VA and the watts are very similar now. See, 39.3 versus 39.9. And that little difference you see now is, again, the transformer loss due to the inductive reactance. But since it is such a small percentage of the total current flowing through the circuit, your VA and your watts are very similar, and your power factor gets closer to 1. All right, if that makes sense. And of course, if I put an even heavier load on there, they would get even closer to one another because this would be even less of a factor in it. So that's how transformers work. Now, here's the thing. Let me disconnect this. If you had a transformer that was, for instance, the core was shorted out. You know how I was talking about the, those laminated pieces that have the enamel on them, or have they're insulated somewhat. They have that enamel paint on each one. If those were shorted out, and if you look, these screws actually have these little plastic sleeves, and that holds the screw in the middle of where this goes through. You notice how much smaller this screw is than the hole. And the reason is they don't want this shorting out those laminations. Because if the transformer core shorts out like that, those eddy currents, once again, are going to influence this. And what's going to happen is you're already using 8.8 VA of energy, okay, or of power, I should say, that you're dissipating in this transformer. Most of that is going to be dissipated into this transformer as heat. Well, what will happen is that's actually relatively low for a transformer of this size. My great big isolation transformer I use on a bench is a lot worse than that. But if this transformer were bad, if it had a lot of shorted laminations in it or something, this would get much higher. This transformer would run a lot hotter, and it would not be as efficient at converting, of the primary to the secondary. It would affect all of that. So if you ever see an old transformer, and when you plug it in, it gets really, really hot, even when you're not really running the amplifier hard or anything, chances are you have something wrong. Either the windings of the transformer could be shorted inside because of the heat, the enamel coating of the wires has broken down, and the windings are physically shorting to one another, or those laminations are starting to break down and short because all of that enamel, or that varnish that they put on the plates, on the each individual lamination, it has broken down, and those plates are shorting to one another physically, and those eddy currents that are in each of those plates are shorting against one another and causing almost like a resistor. It absorbs some of the energy. So, long story short, this is a good transformer. I don't think there's any problems with it. It was just that thermal fuse popped open. I don't see any discoloration. I don't see anything that makes this thing look like it's too hot, or, like it got hot or anything. Because normally this varnish on here would discolor. It turns like a real dark brown color when these transformers run really hot and they overheat. I was worried about that because, if you remember, that paint was all bubbled up on here. But I think that was just because the steel that they used, as the shielding on the outside of this, that steel is just really susceptible to corrosion and rust. And I think that surface rust got under there and just caused that paint to bubble off. I think that's all it was. So I'm going to put this together as soon as this paint finishes drying. And in the meantime, I think we have a good transformer. And after a little bit of cleanup, it's all together and looks good. It's the next day, it's dry. And, well, compared to the old one here, yeah, I need to take that out and clean it. And look how bad that paint is up there. So I'll probably pull this transformer, and since it works, I'll test it and everything, but since it works, I'll leave it together. I'll clean it, and then I'll paint it the same way. And while I have this out, that gives me a chance to clean the chassis. There is no rust, corrosion, or anything on the chassis at all that I can see. So other than, a cleanup, which I think if I just do a little basic cleanup on this down here, I bet you it'll come out really nice. I mean, look at that. Just wiping it with a dry paper towel. That's going to turn out really nice. So I'm going to take this out. I'll do that off camera. I do have the new modules ordered for this, and in the next video we will tackle the task of replacing those, and we'll talk a little bit about how they work, the new ones and so forth. So until next time, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care, everybody. Bye-bye.